Okay, so we want to move away from gases, yay, to liquids. And before we do a mixture of liquids, let's just get it straight how we describe a pure liquid. And a pure liquid, we drew it in a test tube, sort of like this. We opened it at first. There's my pure liquid. And let's call it pure liquid A. And if I make it a closed system, so I'm going to put a cap on it, a closed system, then up here is my vapor of pure A, or my pure vapor. And of course, these are in phase equilibrium with each other, so I can write something like that. And I can write also that because it's at equilibrium, the chemical potential of A, it's pure, in the vapor, by definition at equilibrium, it's equal to its chemical potential in the liquid, because we are at equilibrium. So remember, equilibrium, it's dynamic equilibrium, so there is condensation and vaporization going on, but there's no net tendency for this to happen. That's why the chemical potential is the same. Okay. Now, yeah, okay. So I can write that at equilibrium, then, this chemical potential, which I write as mu, of A, and I put an asterisk here because, and actually, let's do that at the top, somewhere, maybe in the margin. I have three symbols that figure in this chapter. This indicates a pure substance. This indicates ideal. And this indicates standard, so at 1 bar pressure. Okay. So here I have that the chemical potential of pure A is equal to its standard plus RT ln P. It's always RT ln P, but the P here is the vapor pressure above its pure liquid. And this is something, so let's define that, is something that I can find in a table. This is a table value. So I would look it up for liquid A at that temperature that's given. This is the vapor pressure. So water, for example, has a certain vapor pressure at a certain temperature when it's just above its own liquid. So that's something that I can look up. And what I want to do right now is just take a little, it's almost a chapter 4 interlude where we were doing our proofs, just to reinforce something that seemed like it didn't really connect with what we were doing, like I said this morning, but it actually does. And it reflects this pattern here. It's always, the chemical potential is always equal to a standard plus something that accounts for it not being at 1 bar pressure, but at this vapor pressure. So let's just do an interlude for a moment, like we did this morning, and then we'll get back to going from our pure substance to a mixture. Excuse me. So, yeah. Let's start as we did. G is equal to H minus Ts. And H is U plus PV. And so I have U plus PV minus Ts. Therefore, dG is equal to a du, and I know that du is TdS minus PdV. Okay, then continuing, plus PdV plus VdP minus TdS minus SdT. So this cancels with this, or goes to 0, and this goes out with this, so I'm left with, as you well know, dg is equal to, or can derive, vdp minus sdt. So what I want to do at this point is divide by what? What do I want to do? Pressure. Yeah, of course. See, because up here I'm noting that the chemical potential depends on pressure. It's always, the chemical potential for a certain state is always referenced to its standard. So it's equal to the chemical potential at standard pressure plus accounting for the fact that I'm not at standard pressure. So it's depending on that pressure. So that's why I'm, and it's at constant T. So I'm dividing through by a change in pressure at constant T. And what that gives me is dg by dp, constant temperature, v, generate the new partial derivative, okay, minus s, another new partial derivative here. It's dt by dp, constant t. So change in temperature, constant temperature, 0. And dp, that equals 1. Ah, love it. dg by dp, constant temperature, is simply equal to volume. And you're thinking, where are we going? Stay on board. We are moving along in the right direction. dg, therefore, is equal to v dp under constant temperature. It's not apparent anymore because I've removed it. Okay, but the vapor is taken as perfect or ideal. And therefore, V can be written as nRT over P, and I'm going to write it nRT times 1 over P, so that I've got dG is equal to nRT 1 over P dP. And you know what we're going to do next? Oh, before that, I'm going to take this n, divide both sides by n, or flip this over here, and that gives me a change in the molar Gibbs free energy, which is a chemical potential, RT 1 over P dP. Then I want to integrate it, and I know that R and T are constant, and instead of writing delta G, I'm going to say that that's equal to the chemical potential, because that's what a chemical potential is. It's a molar Gibbs in the final minus chemical potential in the initial, equal to RT ln of P final over P initial. Now, this is very general, initial, final. Let's go back up here. I wanted to know, just tell me what is the chemical potential of A. And it's always, well, here's what it is standard, and then account for it not being at standard pressure. So it seems that any time that I want to actually determine a chemical potential of something, I have to relate it to a reference or a standard, and that's true. So look what happens when I isolate this. I get the chemical potential in this final state, or in any state. It's equal to the initial plus RT ln, I was going to write something here, but I'm going to do it down here instead. Okay, so I'm going to continue my story here. So what I do in a thermodynamic context, of course, I choose a path. So if I want to know what is the chemical potential for a given state, I say, let me pretend that this is the result, the final state of a change, and let me make the initial state the standard one, so that the chemical potential of anything, like A above, the chemical potential of anything is equal to the chemical potential under standard condition, and then change it to the condition into which it exists. So what I'm saying here is, let the initial equal standard. Standard state. So in fact, and let the final state equal, you know, my given state for which I want to know the chemical potential. Okay, so this tells me that the chemical potential of any substance, and let's talk about A, it's equal to, my initial was standard, okay, plus RT ln of, now what is the standard pressure? I can hear you answering. You're saying 1 bar. And what is the ln of 1? This is why standard is bar. 1 bar, ln of 1, 0. So, oh, do we have a division by 0? No. This is 1 bar. So what it effectively does is gets rid of the unit, and I'm just left with the ln of the P in that given state. And if you want to think about it differently, the ln of P final over P initial is actually the ln of P final minus the ln of P initial. And the ln of P initial we just said was 0. So either way you look at it, this is just the ln of P final, which we said is just the ln of the vapor pressure in that state. So I'm talking about a pure state, and it's always related back. And lo and behold, that's what I have up here. Isn't that awesome? Okay, that's my interlude. Now, that is my pure state. We are ready to make a liquid mixture. The next part is the last part.